Namaskar students. In this video, we will take some problems based on mean value theorems, Taylor's theorems, Maclaurin's theorems, Taylor's and Maclaurin series. So let us start with the first problem. The first problem is here. We have to write down Maclaurin's formula for the function fx, which is square root of 1 plus x with Lagrange's remainder are 3. So the formula which we have to write here, that is the Maclaurin's formula. So we will be using here the Maclaurin's theorem. We have to use here the Maclaurin's theorem for the function f, which is given by this square root 1 plus x. So this is the given function. And we have to write down this formula with Lagrange's remainder R3. We have discussed Maclaurin's theorem, we have discussed Taylor's theorem, we have discussed the term remainder, Rn. So here we have R3, that n is here 3. So if I write down here the Maclaurin's theorem with R3, that will be, so first of all, write down the given function. We have fx equal to square root 1 plus x by Maclaurin's theorem. We have fx equal to f0 plus x, first order derivative of function f at 0. Next term, x square upon 2 factorial, second order derivative of the function f at 0 plus, now in this term, since we have to write Maclaurin's formula with Lagrange's remainder R3. So here we will be having third order derivative, and this will be, we have to write here remainder R3. So what we will be having here, x is to power 3 upon 3 factorial, and earlier in Rn it was nth order derivative, it is R3. So it will be third order derivative of this function f at the point within this interval. Because in the Maclaurin's theorem, the interval is this closed interval 0x, and the point is lying within the interval. So it will be in this open interval 0x, and that point is theta x, where theta is lying between 0 and 1. So that this point theta x lies within this interval. Now let us evaluate first order derivative, second order derivative, and third order derivative of this function f, and let us evaluate these at the point which is 0. F dash x will be 1 upon 2, 1 plus x raised to power minus 1 by 2. Differentiating it further, second order derivative will be minus 1 by 4, 1 plus x raised to power minus 3 by 2. Differentiating it further, the third order derivative of this function f will be 3 by 8, 1 plus x raised to power minus 5 by 2. So we have evaluated all the three derivatives of this function f because these are required here in this Maclaurin's theorem. Now let us evaluate these at the point which is 0. Now f0, it will be 1. f dash first order derivative at 0 will be 1 by 2. We can put here x as 0 and we can check here that it will be 1 by 2. Now second order derivative at 0, here we have second order derivative, it will be minus 1 by 4 at 0, and we need third order derivative of the function f at the point which is theta x. So third order derivative of this function f at theta x, this will be 3 upon 8. We are replacing here x by theta x because we are evaluating this third order derivative at theta x. 1 plus theta x, this raised to power, whole raised to power minus 5 by 2. So we have evaluated all these. Now let us put it in this formula which we have, in which we have considered remainder R3. We can name this function as equation 1. We can name this as equation 2. We get fx, which is square root of 1 plus x. This is equal to f0. We are putting here in this f0. f0 is 1 plus x. We are putting in the second equation plus x f dash 0, which is 1 by 2. Then we have x square upon 2 factorial, second order derivative at 0, which is minus 1 by 4. Then we have remainder R3, x cube upon 3 factorial, third order derivative at theta x, which is 3 by 8, 1 plus theta x raised to power minus 5 by 2. We get this square root of 1 plus x. This is equal to 1 plus x by 2 minus x square by 8 plus x cube by 16, 1 plus theta x, this raised to power minus 5 by 2. So this is a Maclaurin's formula for this function under root 1 plus x with the remainder R3. Let us take the another problem. The problem is expand tangent x in powers of x minus pi by 4. So we have to expand here this function f, which is tangent x, in powers of x minus pi by 4. Now, let us think here that which result we will be using. If we talk about Maclaurin's theorem or the Maclaurin series, in Maclaurin series, it is in the powers of x. And here we have to expand it in powers of x minus pi by 4. So here we will be using the Taylor series. And why we are using here Taylor series? Because they are not restricting us that we have to find we have to write formula in the form of remainder. They are just saying expand. So instead of theorem, Taylor's theorem, we will be using here the Taylor series. So consider, first of all, consider the function as f. So let us take tangent x as function f. We have by Taylor's series fx, we have discussed that f of a plus h, it can be written as fa plus h, first order derivative of this function f at the point a, plus h square upon 2 factorial, second order derivative of this function f at the point a, then h cube upon 3 factorial, third order derivative at the point a, h4 upon 4 factorial, fourth order derivative of this function f at the point a, and so on. It will go up to infinity. So we will be using here the Taylor series because the question is for expanding and we have to expand it in the powers of x minus pi by 4. Now, if we see this result, this series which is present on the right hand side, it is in the powers of h. So what is our h? Since we have to expand here in powers of x minus pi by 4, so we can see here that this h will be x minus pi by 4. And what will be this a? If h is x minus pi by 4, then this a will be pi by 4. So let us take here h as x minus pi by 4 since we have to expand it in powers of x minus pi by 4. So if we compare here, since it is in powers of h, but we have to expand in powers of x minus pi by 4. So we'll be considering h as x minus pi by 4. And if h is x minus pi by 4, then a will be pi by 4. So if I rewrite this, fx, let us split this x in a and h. A is pi by 4 and h is x minus pi by 4. This is our a and this is our h, a plus h. Replace a by pi by 4, h by x minus pi by 4, first order derivative of the function f at the point a is here pi by 4, x minus pi by 4 square upon 2 factorial, second order derivative at pi by 4 plus next term will be x minus pi by 4 raised to power 3 upon 3 factorial, third order derivative pi by 4. So find at least 4 non-zero terms of the series, and if in the problem they are specifying that expand tangent x in powers of x minus pi by 4 up to 5 terms, so in that case you have to find out the first 5 terms, and if it is not specified then find out at least 4 non-zero terms of this series. So now what we need to find? We need to find out f first order derivative f dash, we need to find out second order derivative f2, we need to find out the third order derivative f3. And after that, we have to evaluate all these at this point a, which is pi by 4. So let us evaluate these derivatives. We have fx here as tangent x. Differentiate it once, we will get first order derivative. It will be secant square x. Differentiating it further, for second order derivative, we will get here 2 secant square x tangent x, and if we differentiate it further for the third order derivative, we will get here 2, if we keep this secant square x as it is and we differentiate tangent x, it will become 2 secant x raised to power 4. Now, this time, let us differentiate the secant square x and let us keep this tangent x as it is. It will give us 4 tangent square x secant square x. Now, let us find out all these f at the point pi by 4, first order derivative at pi by 4, second order derivative at pi by 4, and the third order derivative at pi by 4. So, f at pi by 4, just tangent pi by 4, it will be 1. And first order derivative at pi by 4, it will be secant square pi by 4, secant square pi by 4, and this will be 2. And similarly, you can check, I am writing here directly that second order derivative at pi by 4, it will be 2 secant square pi by 4 tangent pi by 4, it will be 4. And third order derivative of this function f at pi by 4 will be 2 secant pi by 4 is to power 4 plus 4 tangent square pi by 4 secant square pi by 4. It will be 8 plus 8 and it will be 16. Now we have evaluated all these values. Let us put these values in this Taylor series. Using Taylor series, we get fx. What is fx? Fx is tangent x. We are expanding here tangent x. F pi by 4, f pi by 4 is 1 plus the next term we have this term x minus pi by 4, x minus pi by 4, keep it within the bracket because we have to expand this in powers of x minus pi by 4. And then f dash pi by 4, this is 2. Next term, 1 upon 2 factorial x minus pi by 4 whole square. Then second order derivative of the function f at pi by 4, which is 4, plus next term 1 upon 3 factorial x minus pi by 4 raised to power 3. Then the third order derivative at pi by 4, which is 16. And this is a series, so it will go up to infinity. Let us simplify it further. 1 plus 2 x minus pi by 4. This will become 2. Don't open this x minus pi by 4 whole square because we have to express tangent x in powers of x minus pi by 4. So x minus pi by 4 should be there on the right hand side. So don't use here the formulas of a minus b whole square, and don't open it, this x minus pi by 4 whole square. And if I simplify this, it will be 8 by 3 x minus pi by 4 is to power 3. So this will be expansion of tangent x in powers of x minus pi by 4. Let us consider one more problem. The third problem is, if fx is equal to sine inverse x, you have a and b, where a is less than b, and both a and b, they are lying between 0 and 1, use mean value theorem to show that b minus a divided by under root 1 minus a square, this is less than sine inverse b minus sine inverse a, less than b minus a divided by under root 1 minus b square. Now here in this problem, it is already specified that we have to use mean value theorem. Now we have to see that which mean value theorem we have to use, because we have learned Lagrange's mean value theorem followed by Cauchy mean value theorem. Then we have learned generalized mean value theorem, in which we have covered Taylor's theorem and Maclaurin's theorem. So here we can try for Lagrange's mean value theorem. The function is already given. The interval is here. The interval is closed interval AB, where A and B, they are lying between 0 and 1. So let's start. We have fx equal to sine inverse x defined on this closed interval AB, where A and B, they are lying between 0 and 1. Now, by Lagrange's mean value theorem, since we have here A and B, and in Lagrange's theorem, both A and B are involved. So we are using here Lagrange's mean value theorem. Now by Lagrange's mean value theorem, there exists at least one C in this open interval AB, such that derivative of this function f at this point C is equal to fb minus fa divided by b minus a. The result involves first order derivative of this function f. So let us evaluate first order derivative. For fx equal to sine inverse x, f dash x is equal to 1 upon under root 1 minus x square. And we need this derivative at the point C, and here this C, it is lying between A and B. This is lying in this open interval AB. So what we get? We have f dash C, which is 1 upon under root 1 minus C square. This is equal to FB minus FA upon B minus A. So what will be FB? If fx is equal to sine inverse x, FB will be sine inverse B sine inverse B minus sine inverse A, this divided by B minus A, B minus A. If I rearrange these terms, because the result which we have to prove that contains the sine inverse B minus sine inverse A. So let us rearrange and check what is sine inverse B minus sine inverse A. B minus sine inverse A, this will be B minus A divided by under root 1 minus C square. Now, if we see the result which we have to prove, the sine inverse B minus sine inverse A. Here we have B minus A, but here we have under root 1 minus A square, and here we have under root 1 minus B square. We don't have C here. The C, we get the C by applying the Lagrange's mean value theorem. So somehow we will try to eliminate this C and try to get this inequality. So here what inequality we have? Right now we know that the C is lying in this open interval AB. Means the C is lying between A and B. So by this inequality, we will try to prove the given result. Here, the C is lying in this open interval AB. C is lying between A and B. Now, if I consider their square, A square, this will be less than C square, this will be less than B square. Now see here we have minus C square. So if I consider the negative sign, then equality will change here. Minus A square, it will be greater than minus C square, and minus C square, it will be greater than minus B square. And let us now bring here this 1 minus C square. So let us add 1 on here. So there will be no change in the inequality. 1 minus A square, 1 minus C square, 1 minus B square. The inequality is same. We have square root. So let us consider here the square root. That is square root of 1 minus A square. This will be greater than square root of 1 minus C square. That will be greater than square root of 1 minus B square. Now, if I take the reciprocal, on taking reciprocal, the inequalities will change here, and we will get 1 upon this square root 1 minus A square. This will be less than 1 upon under root 1 minus C square. This is less than 1 upon under root 1 minus B square. Now, if we take b minus a in numerator in the above inequality, since b minus a, it is positive, there will be no change in the inequality. We will get, why we are using here b minus a in the numerator? Because the result which we have to prove, that contains this b minus a. And on doing this, the term which is present in the mid, this one, this term, it has the same form, this one. Means it is similar to sine inverse b minus sine inverse a. So what we are doing here, by using this inequality, we are trying to get this b minus a upon under root 1 minus c square. Because this b minus a upon under root 1 minus c square, this is equal to sine inverse b minus sine inverse a. So what we are doing, we were trying to obtain this b minus a upon under root 1 minus c square. In each step, we are proceeding towards the same. And finally, we get this, and if I name this as equation 1, using equation 1, we get b minus a is divided by 1 minus a square. And what is this? From equation 1, it is sine inverse b minus sine inverse a, so it's less than b minus a under root 1 minus b square. And this proves the result. Thank you. Have a nice day.